cold, strong, and precise. After trimming excess length, the steel plate returns to the round bending machine. Under powerful pressure, it's curved into a perfect arc without a single degree of heat. Watching this transformation feels like bending time with metal. With every thunderous strike, raw steel transforms. A red-hot billet is pressed between dies by a 31.5 kilojoules CNC forging hammer, shaping a connecting rod in seconds. Sparks fly, force roars. This is precision under pressure, built for the heart of every engine. Installed at the end of the line, the Divomec LE612 takes over with mechanical precision. Its internal arms lift finished products from the conveyor, stacking them neatly onto transport panels. One by one, each unit is aligned, placed, and layered, like building with logic and steel. Once stacked, operators seal the bundle, label it, and prep it for dispatch. There's no rush, no guesswork, just rhythm and reliability. Watching it in action feels oddly satisfying. In a factory where speed and accuracy matter, this machine delivers both, seamlessly bridging automation and the human touch. Here's how Ford builds its tough car bodies. High-strength steel is stamped into shape in seconds. Robots weld the panels together with millimeter accuracy. It's speed, structure, and strength, engineered to stand the test of time. Want to see what engineering perfection looks like in motion? Step inside the Holroyd 8EX. Each blank, up to 850 millimeters wide, is mounted on a rigid bed, ready to be shaped into complex helix profiles. The CNC system commands ultra-fast spindle speeds and multi-axis motion, cutting grooves with microscopic accuracy. A built-in probe checks alignment before every pass, ensuring repeatability. Chips fly in tight spirals as the tool carves with surgical focus. Each pass of the cutter reveals more of the rotor's final form, fluid, curved, and perfect. Coolant flows constantly to control heat. A single rotor may require hours of machining, but the results speak for themselves. The final geometry? Flawless. Watching this machine in action feels like watching steel being sculpted with code. In the world of compressors and pumps, this isn't just metalwork, it's core performance, carved from raw mass. Lifting thousands of tons isn't luck, it's engineering. To hoist three massive FPSO modules, S20, P60, and P20, each weighing up to 3,669 tons, Julie Sling deploys a full rigging system. Balanced beams, 3,000-ton shackles, and grommet ropes rated for extreme loads. Every piece is inspected, every angle calculated. Even the lifting plan is engineered for precision. Watching those modules rise, slow, steady, synchronized, is deeply satisfying. With forces like this, there's no room for error, only control. From sea to sky, this is how you move steel on a giant scale. Turning heavy coils into flawless, flat sheets. This is sheet metal engineering in motion. The 15-ton coil is loaded onto the decoiler, slowly unrolled with controlled tension. A servo feeder and straightener team up to flatten every curve, prepping the metal for a clean cut. At the end of the line, a guillotine shear slices each sheet to exact specs. Smooth, fast, and efficient. Watching this line in motion, it's like seeing raw force tamed into precision. In the world of sheet metal, this is where it all takes shape. How do you engineer a press brake that redefines European manufacturing scale? This is how Europe's largest press brake is built, step by colossal step. At GWF Mongolei, it begins with massive parts, too large to cast whole, thoroughly welded section by section. The welds, even stronger than the base steel. Each seam undergoes ultrasonic inspection across a 100-point grid, verified by independent experts. No shortcuts. Once welded, machining starts. Frames are drilled, tapped, and milled with micrometer accuracy. A 520 mm plate is bored to anchor the press into its foundation. The piston, a 60 cm giant, is treated with a custom finish for durability. The 16-meter-long table, flipped upside down just to cut precise T-slots. It's wild to think each groove could stretch the length of a room. Every stage demands careful handling, even during transport. On-site assembly requires tight coordination. One side frame can take hours to position, just to meet tolerance targets. It all leads to this: a 40,000 kilonewtons force giant, over 805 tons, as long as a basketball court, and twice as heavy as an A380. Watching it come together is like witnessing mechanical architecture in motion. Not just a machine. This is steel mastery turned into legacy. This is what 800 revolutions per minute of pure machining mastery looks like. This high-speed, 5-axis CNC marvel tackles complex parts with full simultaneous motion. Its horizontal spindle design allows chips to fall freely, no buildup, no delays. That's a game-changer for clean, uninterrupted operation. The demo begins with rough turning. The tool slices through steel while rotating at up to 800 revolutions per minute, shaping the cylindrical base. Then comes contouring, fluid movements that define edges and profiles with micron-level accuracy. Notice the negative tool angle, cleverly applied to reduce cutting forces and extend tool life. This isn't brute force, it's calculated precision. Tool changes happen fast. Without missing a beat, it shifts into drilling and finishing, streamlining operations into a single setup. The result? Less downtime, more output. Slow-motion scenes reveal chips flying cleanly away thanks to spindle orientation, no chip jam, no surface flaw. From aerospace to automotive, parts like this must meet extreme demands, and machines like the G550T make that possible. How does raw steel transform into strong, precision-shaped components in just seconds? Step into the world of Duelin's automated induction heating systems, where raw bars, plates, and gears are transformed with lightning speed. It starts with a full automatic induction hexagonal bar end heating station. The bar is fed, passes through a coil, and glows bright orange as its end reaches forging temperature in under a minute. Seamless, efficient, and repeatable. Carbon steel round bars are next. Immersed in multi-coil setups, they heat uniformly, ready for bending or forming. Flat plates? They glide through high-frequency coils, heating evenly with zero contact. Ideal for prep before forming or welding. Need even heat on irregular shapes? Adaptive coil spacing compensates in real time. Complex geometries no longer mean uneven temperature zones. That means better forming, lower scrap. Pocket. Now, watch the CNC induction roller hardening machine. Rotating shafts pass beneath a coil. Surface layers harden without altering the core. Gear teeth follow, each one scanned and hardened individually for durability under stress. The shaft surface hardening rig ensures spindles and axles can resist wear. Long bar induction machines heat treat bars several meters long, making them fit for presses, cylinders, or rails. Brazing? Dual end delivers. The saw blade and rotor brazing stations melt filler metal precisely. No flames, no warping. Machine tools get the same treatment through silver induction brazing, forming clean, strong metallurgical bonds. The level of control is astonishing. Each second, each coil, each ramp is tuned by software. This isn't just heating, it's science sculpting steel. Everything runs on Duolin's IGBT induction generators from 2 kilowatts to 1,500 kilowatts at 0.5 kilohertz to 1.2 megahertz. With 13 patents and thousands of systems shipped worldwide, they don't just heat, they lead innovation in forging, hardening, brazing, and beyond. Glowing metal, robotic feeders, seamless transitions. This is what modern industrial heat treatment looks like when precision meets power. In the open sea, where nature never rests, precision isn't optional, it's survival. This is how offshore wind turbine foundations are installed. The process begins with transporting and positioning the pile installation frame, or PIF. It's securely sea-fastened to the vessel deck for safe transit. Once at the site, the PIF is lifted and aligned vertically above the seabed. Precision matters. Every degree counts when working in ocean currents. Next, monopile foundations are driven deep into the seabed. These massive steel cylinders are guided through the PIF. Shims are extended to ensure proper centering, then retracted so the hydraulic hammer can pass and begin pile driving. The hammer delivers controlled, high-energy blows that sink the pile to the required depth. To prevent misalignment, sonar and motion sensors continuously track pile orientation. Even slight shifts are corrected in real time. Throughout the process, top-of-pile elevation is measured to guarantee an exact fit for the jacket structure that will later be installed. If tolerances are off, adjustments are made on-site, leveling, rechecking, and recalibrating. After installation, the PIF is carefully detached and removed. Then, cutting operations trim the piles to precise heights using remotely operated systems. Even out here, surrounded by nothing but sea and sky, millimeter accuracy is non-negotiable. Once all piles are in place and leveled, the jacket foundation can be fitted. This critical substructure will anchor the towering wind turbine above the waves. Watching this is like witnessing a high-stakes ballet: steel, water, weather, and technology in perfect choreography. Offshore wind demands more than power. It demands precision, and this is how it's built. Welding massive rolling mill stand. Precision, power, and sparks collide. This is how a modern high-speed laser cutting machine is built from the ground up. Welcome to Kimla, where steel, software, and science come together to create CNC machines that redefine efficiency. The journey begins with a digital blueprint. Designers create 3D models tailored to specific customer needs. These files then travel across the factory's digital backbone to machining, welding, and assembly departments. Steel profiles, thick-walled and heavy-duty, arrive from the ironworks. Plasma machines cut them to shape, while shot blasting ensures smooth, clean surfaces. After that, each profile is welded into the machine's base structure. It's not just strong, it's geometrically accurate, thanks to multi-axis milling that refines every mounting surface to micromillimeter precision. After machining, the frame is transported to the paint shop, where it's coated for both protection and aesthetics. Meanwhile, the laser enclosures are fabricated on Kimla's own fiber laser systems and then bent with precision. Each bent panel is degreased in a special bath to prepare for powder coating, a step that gives both toughness and a professional finish. Smaller aluminum parts are processed with water jet cutters, preserving fine detail without distortion. Control cabinets are assembled in parallel, loaded with PLCs developed in-house and connected to the central system. Ventilation ducts, filter housings, and motion systems are pre-mounted before final integration. Linear motors, magnetic rails, and measuring systems are installed together, forming the machine's core drive. Magnets are shielded under bellows, which also protect sensitive encoder tracks from debris. Assembly unfolds in an automated station flow, with ventilation ducts, electronics, magnets, and protective bellows coming together. Every step is measured, logged, and double-checked. Once finished, machines undergo software tuning, motion testing, and full diagnostics. What's remarkable? Everything, from motors to software, is made in-house. This level of vertical integration is rare, and it shows. These machines don't just cut, they accelerate productivity. What does it take to craft a wrench that defines German engineering? At Stahlwheel, it starts with simulation-based die design, where every curve, thickness, and tolerance is digitally modeled. Forging follows in one of Europe's most advanced facilities. Steel billets are heated and compressed into shape using high-tonnage presses. Sparks fly, metal flows. Each wrench blank is then trimmed, heat-treated, and shot-blasted to achieve strength and surface purity. CNC machines handle the critical dimensions. Tight tolerances guaranteed. The final steps include nickel-chrome plating and laser marking. From raw steel to finished tool, it all happens in Germany. Watching this process is like seeing discipline, technology, and craftsmanship collide. This isn't mass production. It's mechanical artistry. Built to last. Built with pride. How do you lift a 380-ton steel dome without cranes? At Petrofac's Salalah project in Oman, air pressure does the heavy lifting. The dome roofs, each 43 meters wide, are assembled at ground level inside cryogenic LPG tanks. Once sealed, compressed air gradually lifts the roof into position. No cables, no lifting arms, just precision air control. It's safer, faster, and surprisingly elegant. Watching steel float skyward is nothing short of engineering magic.